Hello, this is Masa-aki Haga. Today I'll discuss about the iron drop, which is often a basic problem for electrochemical measurements. Here is the CV measured in non-aqueous solvent. Since organic solvent has a low dielectric constant, their conductivity is low, and therefore the CV peak separation is generally larger than the theoretical value. This large peak separation arises from iron drop. By using the iron compensation, the peak separation becomes smaller and approaching to the theoretical values. The solution resistance increased, peak potential is shifted compared to that without any ionic drop. The potential of the working electrode is controlled relative to the reference electrode, but due to the current flowing between working and counter electrode, potential gradient is created, and uncompensated iron drop remain between the working and reference electrode. In order to minimize the iron drop, particularly in the case of organic solvents or low dielectric solvent, it is important to follow the precautions. First, to increase the solution conductivity by using the higher electrolyte concentrations. Second is to minimize the distance between logging capillary reference electrode and working electrode. Third is to use the smaller working electrode surface area in order to decrease the current values. Let's consider the origin of the iron drop. The left-hand side, the 3-electrode cell, consisting of 3 electrodes, working electrode, counter electrode, and reference electrode. Each interface contains the resistance and capacitor component in parallel. The right-hand side figure shows the equivalent circuit for 3-electrode cell in solution, where the electrode potential is controlled by potentiostat. The circuit between the counter electrode and solution can be represented as the resistance and capacitors in parallel. There is also solution resistance between the working electrode and counter electrode, and separated solution resistance between the CD and the reference electrode, which is brought close to the working electrode by logging capillary, so that circuit can be expressed as a parallel circuit of the resistance and capacitor associated with the charge transfer at the working electrode. The potentials measured here is defined by the initial potentials minus the potential scanned by scan speed V and minus IR, which come from the resistance component between the reference and working electrode. The logging capillary was devised to control the potential by placing the reference electrode as close as possible to the working electrode. Logging capillary was invented by Hans Röntgen in 1900. I talk about the short history of research, how the logging capillary was discovered. Hans Röntgen worked with Professor Fritz Haber, with the famous professors, for development of ammonia synthesis. from dinitrogen and hydrogens. Haber has studied the electrochemical reaction of nitrobenzene at that time. Haber was having trouble controlling the potential due to the large variation in the product of the electrochemical reduction of nitrobenzene, because the potential was varied during the reductions. Lugin, who was in the laboratory, invented the Lugin capillary to bring the reference electrode closer to the working electrode, so that potential of the working electrode could be controlled more precisely. And Haber was able to obtain reproducible electrochemical data for the nitrobenzene reductions. Unfortunately, Lugin died young at age 36. At that time, Haber felt the loss very deeply. Here's just history. Going back to the main topic, Lugin capillary is placed in the potential gradient generated by the current flowing between the counter and working electrode. The capillary behaves like the contact on the slide wire of potentiometers, and the potentiostat maintains a constant potential between the Lugin capillary and the working electrode. Therefore, the actual potential across the interface is error by the amount of IR, where R is the resistance of the solution between electrode and reference Lugin tips. It is important to keep in mind the radius and shape of the working electrode affect the IR drop. The radius and distance of Lugin capillary are examined in detail as shown here. When the electrode geometry changes from planar, cylindrical shape, and spherical shape, the IR drop is worst for planar electrode. Next, I will talk about how to measure the IR drop. There are several methods. There are two main methods, AC method and DC method. Let's talk about the AC method first. The relationship between the working electrode where the reaction occurred and the uncompensated solution resistance Ru can be expressed by the equivalent circuit shown here. At the working electrode, R Faraday and the electrode double layer C Faraday are in parallel, and Ru is in series with them. When this RC parallel and R series circuit is measured by electrochemical impedance method at different frequency, CF becomes zero in the high frequency regions, and Ru can be measured. For example, if Ru equals 2200 ohm and the current flow 10 microamp, the IR drop is 2 millivolt and almost negligible. In the case of DC method, uncompensated solution resistance Ru can be measured by examining the transient response of the potential when the current is interrupted, which is only applicable at a slower sweep rate. After the initial drop, the potential slowly decreases due to the discharging of the electrode double layer. This IR potential drop is correspond to the IR. This method is simple and is incorporated in most commercially available electrochemical analyzers because it requires only a quick interruption of the current flowing in the circuit and the observation of the change in potential when the current is turned on again. However, this method is limited to systems with very slow charge transfer systems. The potential step technique for determining the IR drop is particularly suited to the situation where it is difficult to pass a large current as required by current interrupt technique. The potential is kept as equilibrium varied, so little to no current flow, followed by potential step, resulting in a spike in the current which decay over time. Current transient response after the application of potential powers is expressed by these equations. The IR drop is equal to the difference in current at time 0, the solution resistance. Another IR compensation is positive feedback by using the operational amplifiers. A positive feedback loop which tend to cause the potential start to becoming unstable or to oscillate. Operational amplifiers is package integrated circuit. The device requires two supply, one at plus 15 volt and the others at minus 15 volt, relative to the common circuit point defined as the power supply called ground. Their input and output connections, one side of the output is connected directly to ground. The two input terminals are labeled with the sign as shown here. The top one is called inverting input, and the others is non-inverted input. The fundamental property of the amplifier is that output E0 is inverted amplified voltage difference ES as shown here, where A is open loop gain. The open loop gain is effective infinite, so that smallest input voltage ES will drive the output to the limit deliverable by the power supply. This is one of the full potential start system based on the potential control amplifier to see in other configuration. I'm not that good at the circuit engineer, so I could not explain the detail of this circuit, but from the top, 3 terminals separated current was added. By this 3 terminal, we can apply the different complex waveform, such as ramp or sinusoidal waves. The working electrode potential is given by adding all 3 input voltage, and feedback loop voltage is subtracted. By the real systems, uncompensated IR drop was added. Therefore, by appropriate positive feedback, we can cancel out this IR drop contributions. Now we will consider when the IR compensation is necessary. In the case of quantitative experiments such as charge transfer rate and determination of equilibrium constant, such a case, the IR compensation is better to apply. When the conductivity of the solution is not very good, in such a case also the IR compensation is required. When the current value is very large, in the case of using the large electrode, IR is becoming large because of the current becoming large. Fourth, when the positional relationship of the electrode in the electrolysis cell is far from the ideal, in that case, IR drop becoming larger, so IR compensation is to get the better result. Circuit stability is also important when performing IR compensation. Sometimes oscillation may be induced by potential change when the positive feedback is applied. Here's an example for the circuit oscillation under IR compensations. If too much IR compensation is applied, oscillation of the circuit occurred. The left-hand side, the small second peak beside the main peak was due to the early stage of the oscillation, and becoming right-hand side CB shows oscillation occurred. So the instability in Faraday process with positive feedback control is caused by the process similar to double-layer charging in circuit. During the past 3 years, a series of commentary papers has been published, as shown here, that suggested that IR compensation should be well described when studying electrocatalysts, particularly for hydrogen generation, oxygen generation, and CO2 reductions, and reporting the result of such studies. When large current of 50 milliamp per square centimeters or more are obtained from the laboratory level to the industrial level, a large IR drop is created even if the resistance of solution is small. And whether or not IR compensation was performed makes difference in important parameters, such as over voltage and slope of Tafel plot, which cause confusion in this world. This is a recommendation for IR compensation. 4 linear sweep voltammograms are shown for oxygen evolution OER reactions using stainless steel electrode at slow scan rate, 1 millivolt per second. It is noteworthy that each of the 4 current axes are different. Graph A is the current is plotted without normalizing using the geometric area of electrode. The red data point are 100% IR drop corrections. This LSB curve is varied because current and RE were not normalized. If the electrode area is 1 square centimeters or so, the current obtained is already normalized by the system coupled with the electroanalysis. It is essential to normalize RU too before it is used for IRU drop corrections. If not, the error curve obtained in graph B will be obtained. The graph D shows acceptably IRU drop corrected polarization curve when both current and RU were normalized with the geometrical areas. The correct way of correcting the IR drop is to either having both current density and IU be normalized or not. If RU drop correction is done using as acquired current and as acquired RU value, normalization can be done IRU drop correction without any errors. Therefore, we should know the current and compensate resistance RU are normalized by geometrical area of electrode. And this is a scheme to obtain the correct data. And these B and C is a bad data set. When the modified catalyst working electrode used, there are many different contributions for the resistance. Therefore, important to know how the IR compensation takes place. Generally, after the scan IR compensation, the IR-RU is assumed to be constant, and the value is often measured at OPE open circuit potentials, where no current flow and no catalytic reaction occurred. But in the reality, there are many resistances exist and change during the reaction, so we should be careful for the IR compensation in the modified catalysis case. Here is the actual reported change in voltammetry before and after IR compensations. First example is the AC and square wave voltammetry of cadmium 2+ reductions. Without compensation, the peak is not visible, but after the compensation, the peak is clearly observed. Also, in the case of oxidation of ferrocene in low dielectric constant dichromethane, the peak separation is 224 mV without compensation, which is very large, but after 100% IR compensation, the peak interval is 59 mV, which is close to the theoretical values. Here is the resistivity of various organic solvent and the electron transfer rate between the electrode of ferrocenes listed. The resistivity increased by a factor of 20 from acet-nitrile to tetrahydrofurans. In such a case, quantitative rate constant cannot be obtained without IR compensation. With ion compensation, electron transfer rate between person and electrode is found to be almost constant, regardless of the solvent. Here is the summary. The ion drop due to the uncompensated solution resistance occurred between working electrode and reference electrode. This uncompensated solution resistance can be measured by several methods. Measuring the ion drop or ion compensate measurements can be performed. In particular case, low dielectric constants, organic solvent, or low electrolyte concentration. For scan rate case, quantitative discussions such as electroreaction rate. In such a case, the ion compensation is necessary. Positive feedback compensation is commonly used for ion compensation. However, be careful for the circuit oscillations. Here is a reference, particularly for electrocatalyst. The from 8 to 11 reference is important to know how the ion compensation is affected for the data. This is the end of today's seminars. Thank you for listening.
Thank you, Professor Haga. If you have any question regarding to the lecture, you can contact us. The next webinar, the Professor Haga 14th lecture, we are planning to schedule for the beginning of October.